Great. Okay, we are recording this session, so if you have any difficulties with that, please put a note in the chat. But I think we're coming up to exactly 5 past the hour, and I'd like to start the webinar. So good afternoon, everyone. My name is Shirley Coleman, and I'm speaking to you from Newcastle upon Tyne in the UK. I'd like to welcome you to this ENBIS webinar on digital twins. We're delighted to welcome a very large audience online today, and also, as I said, to be able to record the presentation. It'll later be made available on the ENBIS Media Centre, so you're welcome to have a look at it there. As always with these things, please keep microphones muted during the presentation, and we welcome comments and remarks at any time, and please put them in the chat function, and we'll keep an eye on that all the time. The talk will be about half an hour, followed by an opportunity for questions and answers, and we'll definitely finish within the hour. It's my great pleasure to welcome Professor Mark Girolami to give our webinar. I'll just give you a little bit of background to him. He's the Chief Scientist of the Alan Turing Institute, which is the UK's National Institute for Data Science and Artificial Intelligence, and he took up this role in October 21. Before that, in 2019, Mark was elected to the Sir Kirby Lang Professorship of Civil Engineering at University of Cambridge, where he also holds the Royal Academy of Engineering Research Chair in Data-Centric Engineering. He previously to that was the Chair of Statistics in the Department of Maths at Imperial College London, so an excellent background pedigree here. Mark's going to talk about digital twins, hype or hope, but first of all, I just want to mention that we have the ENBIS Spring Meeting this year on digital twins, and that will be held on the 25th, 26th of May in person in Copenhagen, hosted by the Technical University of Denmark. Please have a look at the ENBIS webinar for details, the ENBIS website for details of this, and hopefully how you might like to register. You don't have to produce a full paper to register, you can submit an abstract, but we are expecting to be able to publish the proceedings afterwards in a journal, and we'll keep you informed of that. But without any more ado, it's my great pleasure to welcome Mark, and I'd like to hand over now, please, to you. Thank you, Mark.
Thank you, Shirley, and thank you everyone for coming and joining and coming to listen to this presentation on digital twinning. And hopefully we'll be able to have some information to decide on whether this is just another hype cycle, or in actual fact, this is a hopeful set of theories, methodologies, and technologies that will help us to face some of the big challenges that we as societies are being presented with. So digital twins. So of course, when we think about twins, we typically consider the whole notion of the identical twin. But when we start to think about digital twins, right, so a digital twinning of some phenomenon in the actual physical world, then the sort of twins that we should be thinking about are not entirely the identical, genetically identical ones, but ones that look something like this here. This is from the film Twins, where they may well be genetically twinned, but physically are quite distinct and physically distinct from each other. But the key point here is that they are nevertheless sharing core genetic components in each of their individual cells. And if we think about the whole idea of twinning, rather than thinking of the digital representation, we can think about a twin as some sort of model at a scale of cost, a scale of size, and a scale of complexity that will enable us to ask questions about the reality that we are considering. And so, for example, what you see here is a model of an aircraft in a wind turbine. So this is a twin of an actual, in this case, passenger commercial jet aircraft, and it's in a simulated environment where there is air flowing over it. There are sensors on it, enabling the engineers studying it to gather data from the scaled down version as it experiences the conditions as defined in the wind tunnel. So this is an example of a physical twin at a scale that enables experiments to be conducted and questions to be asked, data to be gathered, and insights to be obtained. And of course, we see this here as another example of a twin of a ferry in a marine tank here. And so the twinning is not only the physical ship itself, but also the interaction between the ship and the twin, the physical twin of the seagoing conditions. And again, this is at a scale and a complexity and a cost that enables potentially destructive testing to be undertaken. So this whole notion, again, of the physical twin enabling us to understand some of the characteristics of the actual physical reality. And any of you who have studied engineering will no doubt have made little bridges like this out of straws and then loaded them in such a way to understand very simple load-bearing structures. But when scaled up to the actual physical structures, the underlying physics or the underlying laws of elasticity still hold. Moving away, of course, the whole idea of twinning takes us into the biological and the biomedical sphere. And of course, the mouse model is a classic idea where we have a twin of certain biochemical, biological, cellular processes in the human that are reflected in a sort of Arnold Schwarzenegger, Danny DeVito style of twinning in the mouse model in biomedical research. And of course, for those of you who are still paying attention and are awake will say, Mark, that isn't a mouse, that's actually a rat. But forgive me some artistic license here in this presentation. But the key point here is that the whole notion of twinning extends beyond engineering artifacts to physical and biological reality as well. And of course, that biological reality is represented in these what are called artificial humans. So Neon is a subsidiary of the Samsung Corporation, and they have been developing these digital avatars where you have these videos of generated humans who can actually have a conversation with you. And so, you know, moving from the twinning of a reality of a certain subcomponent of humans to the actual behavior and how humans interact with each other. This is something that Neon Laboratories have been developing. Now, of course, there's a very rich history of the idea of twinning, and probably one of the biggest, and in fact, where the whole notion of the digital twin came from was from NASA. And in this case here, of course, there was not only a rudimentary digital twin of the space flight itself, but there was in fact a full twinned physical representation in Houston. This is of course referring to Apollo 13. And what of the sort of digital twinning that is currently active and that we are starting to see? So if I just speak about some of the things that we have been doing at the Alan Turing Institute, where we have been focusing on some of the basic research questions about digital twinning, but also really pushing out some of the implementations with various partners to actual impact and innovation. And some of the areas that we are working on is the development of the theory of digital twins and how they are impacted when you start to connect them together. Do you increase the signal or do you decrease it? What are the underlying principles of building together connected digital twins? What are the underlying theories? We've also been working on things such as the development of populations of individuals and using those in terms of emergent behaviors given, for example, a set of policy enactments. And we are working with a number of government departments. In fact, we had the Minister from the Department for Transport visiting us on Monday, looking at this idea of taking a particular transportation policy and then looking at how a synthetic population would, and what are the sort of scenarios that would emerge given that that particular policy. So this notion of the digital twin of a population actually exhibiting certain emergent behaviors. There have been some quite cool, important and significant applications, but a lot of fun. There is a farm under Clapham Junction in a disused tube line that grows herbs and using hydroponics. And one of the things that the farmers wanted to be able to do was to have a digital representation of the farm. And the reason for that is that the physics of the environment underground is quite different from the physics of the environment above ground. And so a good understanding of how certain, so for example, how carbon dioxide accumulates, how it is moving about, how heat is transferred, how they interact, all are key variables that have, in some cases, quite dramatically different impact on the yield of the crops when you're growing underground. And so what we were able to do is working with that farm was to develop the whole sensor network, measuring the various accumulation of gases, measuring the temperature profiles, measuring the lighting profiles, and so on. And then developing a digital, a computational model of that environment and the sort of crops that were or are being grown, And then again, playing out scenarios and looking at how one would optimize the yield given certain energy requirements and so on. And that's been a very exciting and ongoing deployment of early digital twin theory methods right up to this particular application. And we're now working with groups such as Rothamsted and other agricultural research establishments on developing digital twins for particular types of agriculture. Another one which was really exciting was the world's first 3D stainless steel printed bridge, which is currently spanning a canal in Amsterdam. And again, what we have been able to do is develop a digital twin where we have, in essence, a finite element model coupled to the actual physical structure itself via a large number of sensors that are on the bridge and feeding in to the digital representation. So this notion of the digital twin is a very clear one in this case here. And then we have others that I'll just mention. We're working with the National Air Traffic Service here in the UK, developing a digital twin of their air traffic control systems. And we are working with various engineering companies such as Rolls-Royce on developing, again, digital twin technologies for their high-value engineering applications. I mentioned the whole idea of twinning in the biomedical sciences, and we next week, in fact, will be announcing the launch of a Turing research and innovation cluster right across the UK on digital twinning. And one of the focus areas will be on health, and in particular on cardiac health, where we are partnering with St. Thomas's Hospital here in London, who have a long-standing program of research in cardiovascular computational modeling, and now coupling that with patient cohorts. And this is an example of some of the work that one of the directors of our digital twin research and innovation cluster is working on in terms of digital twinning of the cardiovascular system. I mentioned the 3D printed bridge that we worked on. This was an incredibly exciting project. One, because it was a world's first, and because it was a world's first, there were some basic scientific questions that still had to be asked. What are the material properties of 3D printed steel? And what are the subsequent structural properties of 3D printed steel? And it was really very exciting to be leading on the development of this actual project. And it's very exciting that we now have a digital twin of the structure. And it's if you get the chance to go and visit it in Amsterdam and walk over it, it's quite a sight. But you'll certainly be generating data that would be coming into and being used in the digital twin of the bridge itself. I mentioned to you as well the digital twinning work that we're doing with the National Air Traffic Service, where we are basically developing a digital representation of all of the flight data that are coming across UK airspace, and this is in an attempt to increase the safety of air traffic control across the UK, whilst increasing the throughput and the efficiency of the air traffic service across the UK civil aviation and military, as it happens, airspace. So very exciting, very challenging work. The other one, of course, is that we can digital twin not just physical systems or environmental systems, or the interaction between physical and environmental systems, but social and technical systems. And this is an example here of a study of how passengers would be moving through a design of one of the stations on the new Queen Elizabeth line, which is now in operation in London. And here we have, again, the coupling of data from videos of patient movement, not patient, passenger movement within the station, and their interactions with turnstiles and elevators and so on. And again, of course, we can then start to scenario plan what happens if there are blockages, what happens if there are delays, what happens if there is an emergency, and so on. The big ambition, of course, would be to say, well, I mean, that's great. You can digital twin a ship, and that in itself is no mean feat. You can digital twin an aircraft. You can digital twin a bridge. You can now start to digital twin various people and how they interact with their particular environments. But the big questions, of course, are, what about a digital twin of a city, of a region, and of course, of a country? And so there is this notion of a national digital twin. And I would say that this is a fantastic ambition, but it is an ambition. And there is an awful lot of work that needs to be done at a very basic level before we could really get to the stage of building digital twins that we actually understand and we can use more than just being, some sort of computational tool, but one that really gives us insight into the pressing socio-technical or socio-economic questions that one would want to ask in terms of perhaps public policy enactments and so on. So I would say that at the scale of national digital twins, we are in danger of being captivated by the hype. But I would say there's an awful lot of hope, but it does need ongoing, consistent and sustained fundamental research and working across a number of disciplines and a number of technology readiness levels to get us to the stage where we would actually have something that would be of genuine utility. But we are getting a lot of the infrastructure in place. So here's an example of transportation in a particular region. The information that we can have in digital form is quite spectacular. But I would say that this is a digital twin in geometric terms, and we have a lot of work to do in terms of actually having these as tools that would allow us to ask the really, really big questions about, as I said, policy enactments with regard to transportation and what are the implications on environment, air quality and health outcomes and so on. But the potential is there, but there is an awful lot that still needs to be done. So very, very exciting horizons for us in terms of digital twinning at quite significant scale. The Alan Turing Institute, of course, is leading the way in the UK in terms of the basic research and implementation across a wide area of sectors. But there are other partners and actors in the landscape, like the Connected Places Catapult and the Digital Twin Hub, and of course the various engineering institutions that are developing their own protocols. So a very exciting environment to be working in, and one that we definitely need to be working together to make the advances that we really need. So in terms of ongoing challenges, I think that hopefully I've shown you some of the promise, some of the excitement, but there are many and there are many opportunities. However, there are many challenges that we will need to address, and it really needs the ministry of all of the talents, of all of the disciplines, scientific disciplines, humanities, social science disciplines. It needs basic research. It needs mid-level TRL activity. It needs startups and entrepreneurs. It needs policy guidance. It needs government intervention, and so on. So I would say, yes, there is a lot of hype about digital twins, especially in this era of artificial intelligence. But I think that there is enormous hope. I think that the potential is really great, and it just means that we need to get together and we need to continue to work on the sort of grand challenges that digital twinning can help us to address. So I'll stop there and pass over to the chair to open up for any questions.
Great. Okay. Thank you very much, Mark. That's excellent. And thanks for all those brilliant diverse examples. I don't like the one of the aeroplane. Is that what happens to a plane when I'm sitting in it and it rocks around? It's quite terrifying.
So I remember being in an aircraft and seeing the wings that I could see flapping away. And I got quite concerned. And then my colleague said to me, well, if the wings weren't flapping, that's when you should really be concerned.
Okay, well, that's good. We've had some questions in the chat, but just they're all along a theme that I just want to explore. First of all, it seems that the most accessible aspect of digital twins is the copying of a situation. You know, putting the sensors everywhere and actually doing a copy of what you're observing. But the real, am I right in thinking the real purpose of the twin is so that you can investigate beyond perhaps what you can see? So you might see, you can monitor and look at all the people in the Elizabeth Line station, but you want to see what would happen if there was a blockage or if a door shut or something. To do that, you've either got to have observed that in the past, or you've got to have some equations modeling it, haven't you, so that you can deduce it.
Exactly, and that you know, interpolating behaviours is one thing. Extrapolating to scenarios that have not been observed is really the goal of what we would want. And as statisticians, we know how challenging extrapolation can actually be, especially when you move out of the space of scenarios that have actually been observed. But of course, there is, you know, there are lots of stochastic tools that allow us to do exactly that. And one piece of work that we did, well, not that long ago, we looked at the transportation of people from residential areas to commercial areas in London. And the sort of questions that we wanted to be able to scenario plan was, what happens if a congestion charge is put into force over the long term to commercial activity in the centre of London and so on. And so by developing systems of stochastic differential equations and then running them to convergence, one can actually see what are the sort of stable configurations of commercial activity and, you know, the growth and decline of them and so on, that are plausible and consistent with the assumptions that have been made. And so that in itself is something that is of great value to policymakers in terms of trying to understand what are the plausible outcomes, what are the, you know, what are the plausible unintended consequences that may emerge. So, so digital twinning goes beyond making measurements and characterizing those to actually taking those measurements and embedding them within the digital representation, and then using the digital representation to, in some cases, control the actual physical, or, you know, to play out certain scenarios that would then again have an implication on what one would do with the actual reality. So it's that bidirectional coupling that distinguishes digital twinning from computational modeling or just monitoring itself. It's that combination, it's that synthesis of the two that enables you know, that forward and backward feedback to take place, which really is something that then enriches what we can do and goes beyond just monitoring and goes beyond just computational modeling. And I shouldn't say just, because monitoring and computational modeling are huge challenges in themselves.
Okay, just to I think that you've already answered this question, but just to reiterate it, we've had a question from someone: what is the main difference between a digital twin and an elaborate simulation model? The visualization or the connection with physical elements through sensors or other devices? I think that's what you've... Yeah,
I mean, I think that's it. I mean, the simulation model is one component. The connection to the physics, well, the measurement of the physical or whatever, the actual elements itself is another component. And then there are things like visualizations and so on. The difference between these things on their own is when they are coupled together in a systematic way that gives you something that is more than the simulation and more than the monitoring. So for example, your simulation is based on a model, and we all know, you know, the aphorism of Box, you know, that all models are wrong, some are useful. And when it comes to modeling things, even something as what we might consider as straightforward as an aircraft isn't straightforward, but a bridge. Our understanding of the physics and the mathematical representations of them are typically misspecified. And depending on the complexity of the system, they become even more misspecified. And so you can see cases where you have a simulation model which is misspecified, but coupling it with data that comes from the generative reality then enables you to update your simulation to be more aligned with the generative reality that you are observing. And so this model reality mismatch is something that I would say is one of the bedrocks of digital twinning, and takes you beyond simulation modeling, takes you way beyond actual monitoring itself.
Okay, thank you. We've got a lot of really good questions, actually. I'm going to get all of them asked to you, but just going through them in a particular order here. One aspect that we wanted to explore was you met that nice example of the Clapham Junction farm underneath growing vegetables and so on. Design experiments was sort of started up very strongly from the agricultural scene. So how do you see the role of some designed experiments in that particular context?
I mean, it is absolutely core. And one of the things that I am always emphasizing to certainly my engineering colleagues is the notion that just because you've got data and you can measure it doesn't mean to say there's any information in it about the questions you want answering. And so, observational data is one thing, but the best that you could do is actually to have a well-designed experiment that is optimal in some information based sense to answer particular hypotheses that you have. If I think of some of the work that my colleagues have been doing on bridges, for example, they've been putting, they've been laying very sophisticated networks of, fiber optic cable sensor networks into operational bridges for rail transportation, as an example. That in itself is a huge step forward. It's very much like Lord Kelvin's statement that if you want to understand something and you want to improve it, you need to be able to measure it. So I think engineers being able to get to that stage is a step in the right direction. Of course, putting 180 sensors in a bridge is not going to be optimal, and it may not actually be necessary. And so the whole idea of the design of experiments, design of optimal experiments, I would say is going to be core and a core set of tools for some of the applications that we're going to start to see in digital twinning.
Yeah, that's a really good point then. So you could have DOE in the sensor placement then, I guess. Absolutely.
And in fact, I mean, you're starting to see papers emerging on exactly that, is the use of DOE on sensor, how sensor placement. And you see that, we're starting to see that pretty much more so where, a strain sensor doesn't cost that much. Putting a satellite up in the air that's measuring, proxies of the thickness of the Antarctic sheet, that's quite expensive. And so design of experiments is something that is really core to some of the work that we're doing with, for example, the British Antarctic Survey.
Thank you. I think just see if you want to add anything more to this question. We've been asked, what is the added value of the twin of the 3D printed bridge after design phase? Is it necessary with coupling sensor data with an FEA model?
Yeah, I mean that's a great question to answer, because it allows us to really illustrate and explore what is the advantage. So for one, in many ways, you have kind of moved from the design phase, right? Why? Well, because the thing is, it has been constructed, it is in place, it is being used. So what, in terms of design, the information that you would get is going to be retrospective. But the main advantage of having a digital twin of the 3D printed bridge was so that we could do longitudinal studies to understand the structural characteristics and how the structural integrity is going to vary over time with use.
Okay, thank you. And on a slightly different note, question: do you think there should be any limits to digital twinning in safety testing? There's a growing pressure in defence to move to digital twins instead of expensive actual safety testing of energetic materials, e.g. rocket motors and gun-launched high explosive projectiles, where it is very expensive to get sufficient reliability assurance of new materials and so on, when these items are deployed. So do you think there should be any limits to that?
So so first of all, we are working with DSTL. That is one of the defence science laboratories in the UK, because digital twinning, that is one of the potential use cases. So testing to the limits of operating validity, and I think then the whole area of validation, verification of the digital representation and the coupling with the physical becomes incredibly important. And I think that this is probably one of the areas where statisticians will really, is going to be incredibly important for serious statistical work to be done. And that's why, I said the title of this talk was Hype or Hope, because there is a lot of hype, about the potential use cases in something such as this, but the challenges to be able to safely deploy this sort of technology and use them as tools and as surrogates for actual testing is one. I think we have to be very, very, very careful here. So I would say that absolutely there has to be limits, and I think that the regulatory bodies are going to play very important roles in this regard.
Okay, thank you. Just looking at thinking about statistical aspects. So we've had a question: do you use statistical methods to measure and model the difference between the twins? So if you had a number of different twins, I guess.
Yeah, I mean, the answer is yes. I pretty much view digital twinning through the computational statistics lens, and the applied mathematics lenses. I mean, one example is if you think of the finite element method, which is the sort of standard method for numerically solving PDEs, and you see examples of them as digital twins. And of course, the construction of the finite element method is based on function approximation, and there's no notion of data or measurement. And so one of the things that we did quite recently is redefine the finite element method right from scratch, right, from the mathematics upwards, so that it is data driven and statistical. And we had a publication in the proceedings of the National Academy of Sciences on the statistical finite element method, which enables you. The finite element method is no longer just a numerical method. It is a statistical method, and all of the statistical tools that are at our disposal, from hypothesis testing to model updating and evaluation, can now all be deployed on models whose digital realizations are based on the finite element method.
Thank you. A couple more questions. We've got another 5 minutes or so. Interesting question. What is your view on levels of validation required for digital twins as compared with that of a physical twin, like a model airplane in a wind tunnel?
Yeah, I mean, I think that it's going to be much more rigorous, because a model airplane, it's a scaled down version to some order of the reality. So in terms of the flow of air that generates lift, that's a scaled down version of the reality. But to capture that in a digital representation means that we need to have a far better understanding of what is the airflow, how our vortices shed, and so on. And so that's a much higher degree of knowledge and understanding of, in this case, the underlying physics. And so I would say that the levels of validation for digital twins are going to be, in a lot of cases, way beyond those of the physical twinning.
Interesting, thank you. Last two questions. One about the scale up, I think. Is the larger scale digital twin you mentioned, where you've scaled up from street to city to country level, or from full production, from a part in manufacture to full production, is that similar to the concept of the metaverse?
I think it is. I think it's, you know, conceptually they are both the same thing, you know, to varying degrees. And yeah, I mean, there are some. There is one company in the UK called Improbable, which develops these artificial worlds for gaming. And you know, at a conceptual level, the metaverse, a national, you know, whatever digital twin, share the same basic concepts.
Okay, and the same person was asking this question about design of experiments. Some simulations are very expensive and take a long time. How well is the concept of design of computer experiments known in the digital twin domain? With rabid statisticians such as myself leading the way in digital twinning, I can assure you that we take every opportunity to ensure that our friends, our more enthusiastic friends, understand some of these statistical concepts and the importance of them. Okay, well, that leads nicely into this other last question before there's a comment. How can statisticians contribute to digital twin research?
Oh, I mean, I think that statisticians can and are contributing to digital twin research in a number of areas. So the first, I mean, at the basic conceptual level, we are generating data from some phenomenon in the physical world. We've been talking about design of experiments. You know, what is the most optimal experiment for to ensure that we have the most informative data for the digital representation that codifies the questions that or the hypotheses that we are seeking to test. So I think that statisticians from just about all walks of statistical science and statistical practice have got great opportunities, and there's a great demand and a great need from them, from computational statisticians to, you know, population statistics, to official statistics, to theoretical statistics. I mean, one example, when we were working on the 3D printed bridge, the engineers took the drawings of the 3D printed bridge and then built their finite element model of it. But when you actually look at the real structure, you see that the geometry doesn't reflect at a certain scale the drawings. Why? Because you've got all these random imperfections which have been accumulated as the printing has taken place. And so we ended up working with some stochastic geometers to try to capture the fact that in actual fact, what we've got is a random, you know, the surface of the structure is a random field. And so, you know, a whole load of spatial statistics is going on there. So I would say that, give me a statistician from any area of statistics, and their contributions. I could point them in a worthwhile direction as far as digital twin research and development and deployment and use is concerned.
That's lovely, and that's a very good note to finish on. So there's a terrific lot of scope. There was someone was just asking if you had a literature reference for the finite element project that you mentioned. I think the rebuilding from scratch.
Yeah, if whoever is asked just emails me, I'll send various links.
Okay, lovely. So I think I should stop there because we've really picked your brains and we've had lots of. But I have covered the questions that have come, so it's really interesting, and thank you very much. Very much enjoyed the webinar. So thank you very much. We can sort of give the clap in the usual way, I think. Just before we all close, I just want to mention that the next webinar in our series of ENBIS webinars is on Wednesday, April the 12th at 12:30 Central European Time, and that's by Rémi Coulard of SNCF France, looking at modelling and forecasting of railway operation and passenger flow variables in dense traffic areas. So another interesting talk, but Mark, that's been brilliant. Thank you very much, and thanks for your time, and thank you everyone for attending.
Yeah, thank you all. It's been great, and I'm very happy to follow up via email with any questions.
Perfect.
All the best. Bye-bye.
Okay. Bye-bye. Thank you.